Awesome. Thanks very much, everyone, for attending today. So geochemistry is obviously a pretty huge topic. I'm not going to be able to discuss everything, but I'm going to focus today giving an introductory talk on a range of the things you can do with multi-element geochemical suites that you can get from your standard lab and run on diamond core or RC or rock chip samples that you're collecting during exploration. So these can really add a whole lot of value in a number of different ways. But I'm going to be really advocating for trying to show people how they can make the most use of all the elements you can get analysed for these days, but in a geologically informed way, where you're putting that geological context on your interpretations. So, yeah, and I'll acknowledge Scott Halley, who's been a real proponent of this approach of using multi-element geochem in exploration for quite a long time now, and a number of you have probably heard of him. So I learned a lot of my stuff from him, and he's got me my last two jobs. So yeah, big acknowledgements going out to him. I'd also like to give an acknowledgement of country. I'm presenting to you today from Sydney, which is the home of the Gadigal people, who are one of 29 different peoples who inhabit the Sydney area and belong to the Eora Nation, Eora meaning here or from this place. So I pay my respects to elders, past, present and future, who hold the memories, the traditions and the cultures and the hope for Aboriginal and First Nations people here and right across the world. Some other people to acknowledge, there's Scott Halley's webpage address if you want to go and check out. He's got a whole bunch of presentations and other resources, tutorials and workflows for dealing with example data sets. So if you're keen to follow up more, that's a really great resource. I'd like to thank Evolution Mining, who I work for allowing me the time to be able to undertake this presentation. And yeah, really is a great company to work for. I've really enjoyed my time here. I've had some fantastic opportunities and got to work with a great bunch of people. And also another acknowledgement, I'm going to be showing a lot of graphs from a program called IAGAS, which a number of you have probably heard of before, but this was originally developed by a company called IA Global, which has since been bought out by Index. But a lot of the key people are very much still there, all the same support and development people. And this is that software program in particular has been kind of allowed a bit of a renaissance of the use of geochemistry in exploration, just for allowing people to do things so much more easily and quickly, and getting to know your data much better than you really could before. So for an outline of what I'm going to talk through today, I've just got some quick key messages up front, and then I'm going to talk through and give some examples of different type of multi-element geochemical approaches you can use when you get full suite geochemistry. Talk a bit about some considerations with sampling and analysis. I'm not going to be able to cover everything, but just some key things that are really important to know, and a few notes on some aspects of data and visualization that either get on my goat or I think are really important. So first of all, remember context is everything. I'm going to be talking about geochemical data today, but it's super important to put that in geological context. And that's about understanding mineral and element behaviour, understanding and thinking in terms of geological processes, geological relationships, timing relationships, but also non-geological aspects. So, how the sample was taken, aspects of the geochemical analysis, and how humans can really mess up with data, and geologists in particular are pretty good at this. So the multi-element geochem approaches that I'm going to talk through are lithogeochemistry, which is where we're using a mobile trace elements. And when I say a mobile, I'm talking about elements that will not move around easily during hydrothermal or weathering related processes. So they hang around in the rocks, and they're robust to those secondary processes. So where we're using those trace elements to classify and understand the differences in composition of the rocks we're looking at, so that we can then use that to be able to correlate different units, to recognize and separate out units that may look visually very similar, or in terms of the major elements very similar. And also look at quote unquote fertility indices, which is definitely a fad that we're going through. Alteration geochemistry, where we're looking at majors and mobile trace elements to understand hydrothermal alteration processes and map out the different types of alteration minerals, processes, and their intensity. Pathfinder Elements, so where we're looking at the concentrations of particular trace elements that are mobile and tend to form fingerprints or footprints around gold or metal deposits, and understanding these can really help us navigate towards ore, or help us understand where we might be in a system. And I'll mention just very briefly some application on geochemical or mineralogical domaining that can be really useful from a geometallurgy side of thing, which is an increasingly popular topic these days as well. I guess the note there is that having consistent quality data that's with a near total digest, like a 4-acid digest, and preferably analysed with ICP-MS, with a good distribution, appropriate sample spacing is really important to being able to get the most out of any of these techniques. So, sorry, I'm just going to move my screen a little bit. So to talk about lithogeochemistry, as I mentioned, here we're talking about using a mobile trace elements that are resistant to hydrothermal alteration processes. So they're relatively insoluble in hydrothermal solutions or in groundwater during weathering processes. The reason why using these are mobile trace elements is useful because there's a lot more of them, and they show a greater variability in how they behave than the major elements. So we're actually able to pick differences out and discriminate different rock types on the basis of their trace element geochemistry that we just wouldn't be able to do with our major element geochemistry. Not to mention that most of the major elements are also relatively mobile and move around a lot during those secondary processes. So I've never had a circumstance where lithogeochem hasn't added value. Again, you always want to integrate it with your geological logging and your other data sets to get the most out of it, but it always helps. So, this image over here, I'll just put my laser pointer on, is showing what are the key controls that determines how elements behave and the patterns that we see in those. So here we're looking at the ionic charge of an ion versus the ionic radius, and so we'll see things that are clustering on this graph are things that will tend to behave similarly. And usually what that means, you're looking at where the major elements are sitting, and then the trace elements that have a similar ionic radius, ionic charge, will usually behave similarly and tend to substitute into the minerals that those major elements will go into. So mineral chemistry and behaviour. Usually here, so we're talking about looking at a couple of different types of elements. Those that are compatible and incompatible. And usually when we're doing a lithogeochemical discrimination plot, we'll plot one of these against the other. But what I'm talking about with compatibility here is the propensity of elements to go into a particular mineral that's forming. And so understanding lithogeochemistry and being able to interpret the patterns that you see, it's really important to have a bit of a context for the kind of minerals that are forming during geological processes, and how and the behaviour of particular elements with respect to those minerals that are forming or dissolving during geological processes. So compatible elements are elements that tend to substitute into usually early formed and higher temperature formed minerals, if we're talking about igneous fractionation, which is often, usually where we're dealing in environments that are where we have a lot of igneous rocks, whether they're volcanic or intrusive, and so these igneous fractionation processes are a really important part of understanding what's going on with the composition of our rocks. So with compatible elements are those that tend to substitute into early formed and higher temperature minerals, which means they have high partition coefficients. So they'll have a higher concentration in crystals that are forming early over the concentration that's remaining in the melt. And we can think about this in terms of associations with different elements. So those trace elements that tend to follow magnesium around are things like nickel and chromium. And so they will generally substitute preferentially into crystals like olivine, minerals like olivine and pyroxene. Trace elements that have an affinity for iron and fairly stereophile are things like scandium, titanium, and vanadium. So they'll follow iron into minerals like pyroxene, amphibole, and magnetite. And then strontium, though that is mobile, will tend to go into plagioclates. Some incompatible elements are ones that tend to hang around in a melt and don't go into those early form minerals. So they will tend to increase in concentration through the fractionation, igneous fractionation process. So what we're talking about here is some really useful ones to use are the high field strength elements, so things like zircon, thorium and niobium, also rare earth elements. These tend to go into later formed phases, resistate phases, like zircons, phosphates and titanite. So usually what we'll see with the patterns that we see in this kind of data from rocks, so if we're plotting a compatible element up here on our y-axis and then an incompatible element on our x-axis, we'll go from relatively high concentrations of things like titanium and other compatible elements down to, and as we drop in the concentration of those elements, and will tend to increase in concentration of the more incompatible elements. So usually, one of the best ways to split out the differences that you're seeing in the composition of your rock units is plotting these against each other. So fractionation processes. I've already mentioned the importance of igneous crystal fractionation. But just to touch on that a bit more, what we're talking about here is when we have a magma and it starts to cool in some kind of lower below crust or crustal magma chamber, we'll start forming these minerals like olivine or pyroxene, and usually they're denser than the melt, and they will start sinking down into and accumulating at the base of those magma chambers. So the thing is, these minerals will suck up trace elements at a greater rate than some other trace elements. So if this was olivine or pyroxene, we'd expect a lot of our nickel and chromium to go into these minerals, and that will deplete the remaining melt in those elements, and then it will concentrate them at the base. So firstly, we have minerals preferentially going into, elements preferentially going into minerals and then being physically separated from the rest of the melt. That can then move away or has change in net composition. So we might get that happening initially with some olivines, or we might have pyroxene or hornblende doing that, and then some other later form mineral, and we'll gradually change the composition of the melt as we go through that process. We can also see other fractionation processes. They can be mechanical processes during within epiclastic sediments. We can also see things like dilution by veining in our samples if you've got a lot of veining in them. So one example of what that looks like in the geochemistry is an example from a fractionated dolerite sill in the eastern goldfields. So we might have a starting composition in that magma around here, and as that starts to crystallize pyroxene and olivine, we'll see the cumulate of that having elevated concentrations of chromium in it, but the remaining melt will be pushed to gradually it'll have lower chromium concentrations, but mineral elements like thorium, that's relatively immobile, will be gradually more and more concentrated within the remaining melt. So we'll change the overall composition of the magma to maybe a leucogabbro after that. What you might then get is that a change in the mineral that starts fractionating, and we start producing magnetite that then settles out and separates from the melt as well. And so what we'll see that magnetite cumulate will have really quite much higher concentrations of things like vanadium and titanium, and the remaining melt will be relatively depleted in vanadium and continue to increase in thorium and zircon and elements like that. So how we can see that fractionation process in a bit of a microcosm is like this. These are downhole plots of those different elements. So you can see the bulk composition usually right near the top contact of the sill, where we're seeing magma that's been frozen before it's had a chance to fractionate. And then we'll see these cumulate zones where we've got relatively high nickel and chromium and things down the bottom. As we move up through a sill and start getting magnetite fractionation, we'll get really high vanadium, and then the remaining melts from that will be strongly depleted in things like vanadium, but we'll see a gradual increase in the concentration of incompatible elements like zircon in those last fractionates within those sills. And so you can then plot that out and map out essentially the internal stratigraphy within those sills and areas where you might be getting better development of the final quartz magnetite dolerite, the granophyric dolerite, which is usually the last phase, and is often a preferred host rock for gold deposits in the eastern goldfields. One of the reasons we want to do lithogeochemistry that's really useful is that it can allow you to discriminate rocks that otherwise look very similar to each other. This is an example from the Mount Carlton high sulfidation epithermal deposit in Queensland, and where there we see some quite broadly developed and very intense hydrothermal alteration that basically blitzes the rock, so that once it's been altered by advanced digital alteration, usually it's just a mixture of quartz and clay. It's very hard to differentiate what it is. So we went in there when I first joined Evolution and did some lithogeochemistry and differentiated out two different rhyodacite horizons that were advanced argillic altered. But in some places, these had not been differentiated properly, and in places, drilling had drilled through stratigraphy and tested this top rhyodacite, but then the hole had been stopped because they thought they'd tested the main ore hosting horizon, when actually the lower rhyodacite was still down there below where they drilled the hole to. In the eastern goldfields, an example of where we can differentiate our otherwise very similar looking rocks is with different types of basalts. So this is an example from from our Mungari project. These are all basalt samples, but on the basis of the titanium thorium ratio, you can pick out these different types that sit at different positions within the stratigraphy. So in comparing that to logging, obviously, logging is an absolutely critical part of it, and there's things you can see visually in a rock that you might not be able to see in the geochemistry. But often in the geochem, we've got a data set that's relatively more objective in some ways, and can allow you to get a much more consistent classification of the rock type than you might get with relatively inexperienced or varying geologists and dealing with a range of altered and weathered samples. So this is an example here, again, from the Mount Carlton project, where all of these samples here have been logged as iridesite because they're all smashed with hydrothermal alteration. But actually what we're seeing in rocks that have been logged as iridesite is the full spectrum, right from genuine iridesite through to intermediate and mafic rocks. It's just that they've been really strongly altered to the point where the geologist couldn't tell the difference. Here's another example from a different deposit. All of these samples have been logged as quartz diorite, but we're seeing things right through from ultramafics to fractionated iron tholiites to andesites and dacitic composition materials. And the similar thing here with what have been logged as mafic dikes, showing a full compositional range. Another thing that you can do with lithogeochemistry is apply it to soils as well, not just to rock chip samples. And where you've got residual soils, you can usually create a pretty decent geology map or assist you in building your geology map from the soil. So this is one example where I've made a ternary image of titanium to cesium to thorium through here, and you can see that it's mapping out some different geology through here quite nicely. And in particular, we can see this quite prominent boundary between the more mafic titanium-rich red group through here, and we're seeing in this area where we've got a antimony soil sampling, you can see that the anomaly there is being truncated quite clearly by that boundary. So that's an unconformity that's defining pre and post mineral rocks. A couple of to-dos or don't-dos with lithogeochemistry. You often see a lot of people and they'll try and classify things on the basis of published rock classification diagrams. I don't recommend you do this. Often they were built with specific purposes that aren't necessarily appropriate to your data set or the composition of rocks that you're seeing. And also, something that people will often tend to do is cut groups and define groups on the basis of those hard lines. When you can see here on this point density contour that we're actually, if we cut these rock groups along these lines, firstly, we'd be including things from that group and that group in the same thing, which are different populations, and also we'd be cutting those two populations in half. So classify on the basis of populations within your data, not on the basis of lines on someone else's classification diagram. The other thing we can do with multi-element geochemistry is look at fertility indicators. So usually what we mean by this, it's usually around igneous rocks, around intrusive rocks that are thought to be genetically related to and spatially associated with mineral deposits of some type. So the classic one here is porphyry deposits. So we're seeing a cross-section showing the overall processes that are involved in producing some porphyry, copper plus minus gold or moly deposits, and all the processes that are involved in changing and getting the composition of the magmas to be able to release a hydrothermal fluid and produce that deposit. So usually what we're looking for here are geochemical indicators within in the chemistry of intrusions that are reflecting the formation or not of particular minerals that reflect some important characteristic of the magma. And usually that's to do with what we're trying to detect is where magmas have been wet, and usually where they've been, in the case of porphyries, where they've been relatively oxidized. It'll depend on the metal and the type of thing you're looking for, but like almost all intrusion-related deposits, you want to see indications that a magma has been wet, and that's affected the crystallization order of minerals. That then has an impact on the chemistry of the resultant magma that you see. So for an example of that here is what might look like quite a complicated diagram, but what it's basically showing us is that as a function of the pressure of water, so essentially the water content and temperature, what minerals we would expect to be seeing. So if we start with a melt out over this side, and then these lines define when you will start as you cool, so you go from right to left, when you would start expecting to see those minerals forming. So if we had a magma that was relatively low in water, so about 3% or so, as we cooled that magma, we would expect to see plagioclase and pyroxene forming before we start seeing magnetite, and we're probably not going to see hornblende forming. Whereas if we have a magma that's quite high in water, so it has 6% or so water, we're going to see quite a different fractionation sequence. And in particular, we're going to start seeing hornblende will start crystallizing before we get either olivine or pyroxene or plagioclase. And we're also going to see hornblende before we get to magnetite as well. And so what we then see with that is that by having hornblende fractionate early, we will pull out our scandium out of the melt. But because we're doing that before magnetite, we're going to continue to let vanadium build up in the melt, because vanadium would go preferentially into magnetite and get depleted in the melt normally if we had magnetite fractionation. So it's really picking that difference between where we're getting magnetite coming in before or after hornblende. And so that's what this diagram is showing here. This is an example from Scott again. So with magnetite fractionation, as we decrease in scandium, as we're getting more and more fractionated, more felsic, we would see the vanadium over scandium ratio also decreasing as we're crystallizing magnetite. However, if we've got wet magmas, we would expect to see that ratio increase. So the intrusion that'll be prospective for porphyry deposits that are relatively wet, we would expect to plot up here. So we can discriminate those two out, but this is all really going back to the geochemistry reflecting geological processes that are happening within those magmas. Alteration geochemistry is another thing that we can do. So here we're more looking at the major elements. So potassium, sodium, calcium, magnesium, iron, those kind of things, which will tend to move around, are hosted in our major silicate minerals. And so with looking at the geochemistry in various ratios, we're able to map out different alteration-related processes that might be happening in these rocks, and also the intensity or the extent to which they've happened. So this is a common diagram here that we can use, which is plotting the molar ratio of sodium over aluminium against the molar ratio of potassium over aluminium. And so on this, we can plot where pure minerals would plot if we had just those pure minerals analysed. So albite will plot over here because it's got there's no potassium in it, and there's one one atom of sodium for every one atom of aluminium within the chemical formula. K-spar or biotite will plot up here. Muscovite would plot around 0.33, illite a little bit lower, and down at 0.0, we expect to see things that could be either be kaolinite or chlorite. Usually most rocks will plot somewhere out here. The more mafic rocks in this area, out as they get more fractionated, they'll plot up in further in this direction. But the trends we see associated with different alteration assemblages will usually travel in different directions. And so if we're seeing albite-related alteration, we'll see samples move out in this direction towards the albite node. If we're seeing illite or white mica or sericite alteration, we'll tend to see things move out in this direction, case bar move up this way, or if it's kaolinite in weathering or argillic alteration or chlorite, we might see it move down here towards the origin. So the important thing to remember with this is that we're talking about Bock rock chemistry here, that the distance something moves is proportional to the relative alteration intensity of that type. And also that we talk about this in respect to minerals, but it does not mean that those minerals cannot be present in rocks that are plotting here. So you can have sericite alteration in a rock that's still plotting with the same overall potassium over aluminium ratio. But what it means is that has been isochemical on a whole rock basis. So it's only used the potassium in the rock to create that sericite. It hasn't added any extra to do that. So these can have sericite, chlorite, albite, whatever in them, these rocks here, but it's only using those components that were originally in the rock rather than adding them, which is what you're doing as you travel along these lines. And so there's a whole bunch of other diagrams like this that we can use to map out different hydrothermal alteration zones around our projects. So to show an example of that, this is from the Waihi deposit, which is a low sulfidation epithermal deposit in New Zealand. And so, we've done a classification, the Barker et al. Have done a classification here on the basis of those different groups. So where we're seeing adularia alteration, illite, smectite, kaolinite, and least altered in the blue. And you can see here, this is just plotting that over the presence of veining within that high sulfidation, that low sulf epithermal deposit. And you can see, so where you're seeing a lot of adularia in a zone that's defined around this area of increased vein density through there. The other thing we can do with this is look at the relationship between what we're mapping out in those major mineral alteration mineral groups and see what the relationships are with our Pathfinder elements as well, because usually we'll see similar patterns between those minerals, which gives us a more robust understanding of the architecture of the hydrothermal system. So in here we're seeing, where we've got the adularia dominant, we're seeing more arsenic, more antimony, and more thallium. But interestingly, so where we've got kaolinite alteration, which is probably steam heated alteration sitting at the very top near paleo surface environment, is where we're seeing elevated mercury, which is what we'd expect there. Another thing we can do is look at mapping out differences in the mineralogy through our deposits. So this can be useful for a domaining point of view once you're getting into more advanced projects and need to start thinking about the properties of the ore, whether it's hard or soft, it's going to produce a lot of clay or not, and what is associated with the gold. And whether it's going to be relatively easy or hard to leach that gold out of the rock during processing. So this is just an example from Pajingo, where we've got a ternary diagram just from samples of mineralized veins. And we can do a point density plot in the ternary diagram from gold to tellurium to silver, and we can see different associations that are sitting in there. So we see, there's a bit of a cluster here that would be defining electrum association around with 2-to-1 gold to silver, but then also there's a node here sitting around hessite, so where we're seeing gold, but it's in association with that hessite telluride, which can increase your reagent consumption and potentially decrease your recovery. And interestingly here, so we can look through these different ore zones along through the Pajingo low sulfidation epithermal vein system, and see that we're seeing changing associations through those deposits. So potentially, so from Vera, we're seeing more electrum dominated. In Vera South and Jandam, we're seeing things plotting around that hessite node more. So there we're seeing changes in those mineralogical associations that could be associated with different properties when we're processing those different ores. So to jump now to Pathfinder elements. There's a pretty typical suite of about 10 or 11 elements there that I always like to analyze for. And so what we're usually looking for with Pathfinder elements and need to be thinking about is what's controlling their distribution, what kind of geological processes. And so most of these elements, or a lot of them, are governed by how they substitute into pyrite. So thankfully, pyrite's a pretty common mineral. It's usually, compared to a lot of other minerals that might be hosting trace elements, is relatively homogeneously distributed through a rock mass, depending on the style of deposit you've got, which means that we can pick up these changes in concentrations of these different elements relatively easily. And so the two things that usually have the biggest impact on the substitution into pyrite of these elements is usually temperature, and also pH is another important one. One thing to remember with Pathfinder elements, though, as well, is that, so here's from Scott Halley on his website again, is some good baseline ranges to use for plotting different Pathfinder elements. But every mineral system is a little bit different. So start with these, and then you may find that you need to modify things. So to look at the typical patterns that we often see, this is an example from a porphyry system where we've got porphyry copper moly style mineralization through here, forming relatively deep and around apophyses off a batholith below. As those fluids travel up through the system, we tend to see a zonation from elements that substitute into, form higher temperature sulfides or substitute into pyrite at relatively high temperatures, through to those that tend to substitute in at relatively low temperatures. So going from things like moly, tin, bismuth, tellurium, through to things like arsenic, antimony, and thallium. So this is defining a temperature gradient, and we often see, particularly in the porphyry epithermal environment, these temperature-based zonation patterns within the Pathfinder elements. An example of where we're seeing pH-controlled patterns is around the behaviour of things like zinc and manganese within those kind of systems. So we tend to see in the middle of the system through here, and where we're dealing with, as we get cooling, we get more acid fluids within which manganese and zinc are relatively mobile, so they stay in solution, they don't get precipitated out. But then near the edges of that system, where we tend to encounter pH gradients, where we might be seeing mixing between these increasingly acidic magmatic sourced fluids versus circulating higher pH groundwaters. And so on those pH boundaries, where we're going from lower pH to high pH, is where we'll start seeing higher concentrations of things like zinc and manganese being precipitated out. That may be into pyrite, or maybe into other things like sometimes you can get quite a lot into chlorite or carbonates as well. So another example of that here, looking at these Pathfinder elements where we're seeing that, this is the Mount Rawdon, which is a kind of epizonal intrusion-related gold deposit in Queensland. So the ore body is shaded out here in grey, and we can see that it's associated with this kind of central plume of bismuth and elevated bismuth, tellurium and sulfur. Gold's most closely associated with bismuth, which is something we often see in these intrusion-related systems, but then it's zoning up to get increasing concentrations of arsenic, silver, lead and zinc up the top, and we see these halos of elevated manganese and a bit of zinc around the outsides as well, where we're seeing these sitting in chlorite and carbonates associated with that pH gradient. Pathfinder element footprints, particularly when we're talking about orogenic styles, there's, I guess, often people emphasise how restricted the alteration halos can be around orogenic gold deposits, and that can be true in terms of their proximal alteration, but usually these things are sitting within hydrothermal cells that have much larger footprints. So this is an example here of a data set from the Kalgoorlie area where you can see, so everything that's red here is where we've got antimony above about 3 or 4 ppm. And so all the big gold deposits and gold camps through here sit within plumes of antimony that are also usually where you're seeing broad zones of carbonate alteration as well. You'll see here though that there's quite a range in the size of those. There's a host rock control to that, where we see this in mafic rocks. They tend to be more restricted relative to the size of the camp, the size of the gold deposits, compared to things like Kanowna Belle, which is 7 million ounces, but has this huge halo around it. Whereas at Kundana, where we've got about the same gold endowment, but a more restricted yet still large halo around that. So when you're interpreting these kind of patterns, you need to be thinking about controls of host rock, permeability, the buffering capacity of the host rock. If we zoom in on the Kundana type deposits, the other thing we can use pathfinders for is different pathfinders often will have different scales of footprints or different associations around deposits. So we're just talking about the importance of antimony, which we can see over here. This is a zoom in here where we're seeing quite a broad area that's bringing us into the kind of camp scale there. But when we're trying to start looking at zoning towards a particular deposit, we might be looking at different indicators. So in this case, it looks arsenic, tungsten, zinc, and sulfur are more useful for kind of proximal vein related elements. So we're kind of seeing that here. We've got this nice big halo in the antimony, but then when we look at the arsenic in this case, so the Frogs Lake deposit, we're seeing quite a tight relationship there along the ore hosting structure. Regolith is another really important thing to be thinking about as well. So, and the behaviour of different elements in this. So a lot of you, if you're from Western Australia, will be familiar with, the deep weathering environments that we get over there, where a lot of elements, those that are low valence state, will tend to be leached out of the upper parts of the weathering environment, as we would see for copper in this example, where we're seeing this leaching out of the upper part of the weathering profile. Then we've got a supergene enrichment horizon where that's being reprecipitated, and then the bedrock concentrations underneath that. So things like copper, lead and zinc will tend to behave in that way. But some of our other pathfinders, things like tungsten, moly, arsenic, bismuth, tellurium, that are higher valence state will tend to be less soluble in the oxidized acidic groundwaters that are leaching this copper out. So this is the same porphyry copper gold deposit, copper moly deposit, you can see that the copper's been leached out of that surface environment, whereas the moly's been retained. So if you're doing surface sampling and looking to define anomalies, you need to understand the different element behaviour in the context of the regolith there. I've run a little bit over time, so I'll just skip through some of this a bit more quickly. But just to talk a little bit about sampling and program design. So it's really important when you're looking at using geochemistry for some of the purposes we've discussed, that you need to think about two things really, and that's what kind of analysis method are you going to use, and that's going to define what you're able to do with that data. And the other thing you need to think about is program design. So what scale do I need to either map out the hydrothermal cells that if that's what I'm trying to do, or if I'm trying to map drill targets, what's the scale that they occur at and the scale of the anomalies I expect to see associated with it, to define what your sample spacing is going to be, whether that's downhole or in soils or end of hole RAB, that kind of thing. You also obviously need to be thinking about your regolith environment and sampling methodology as well. So for all of this, I'd say that in most cases, a 4-acid digest analysis at a good lab, there is quite some variability between labs in the quality analysis you get. But 4-acid digest with an ICP MS finish for your trace elements is usually the best way to go if you want to do any of this kind of stuff. You can cut down your analysis suite, but usually it's only a relatively incremental cost saving that limits what you're able to do with the suite. In terms of the spatial distribution of the sampling you're looking at, try and cover the whole of the mineral system, or at least to define background relative to what you're looking for. So if you're trying to define zones for targeted drilling on a particular structure, you need to make sure you're covering a significant length of that, so you can define what's high, low, what's background. With program design, usually you can get away, if you're trying to map out mineral systems initially, you can get away with some quite broad spacing, but it does depend on the geological environment that you're in. And if you're trying to define drill hole targets, usually closer spacing is better and more important. To touch on that with an example, this is one from the Mount Carlton deposit where I worked some time ago. These two diagrams here are called RGB images, percentile cutoffs, where we're looking at 3 different trace elements that have different associations, proximal through to distal, so we can map out where we think we are, proximal, distal, more highly or less eroded in the mineral system. You can see both of these images are pretty much the same. So we're mapping out things pretty much the same between these two. Thing is, though, this is the original data set, which is mainly 100 to 200 metre sampling, spaced samples. That's 14,000 samples at an assay cost of $400,000. We could get pretty much the same map in terms of zoning into where we want to do some more concentrated follow-up work with 400 metre spaced sampling, which would mean 1/10 the number of samples and the cost, and significantly the amount of time that it would take to do this. So you really want to be thinking about what is the scale I need to be able to define the patterns I'm looking for. When we're looking at analyses, digestion is a really important thing to consider. So usually when samples are being analysed, they're being digested into a solution so that can then be be run through a machine like an ICP-MS or an ICP-OES. But the type of digestion you use, which is basically mixing up powdered sample in a concoction of acids, the type of concoction basically will determine how much of that sample and which minerals you're going to dissolve. And so that's a really important consideration, because if you want to look at things like your trace elements for doing lithogeochemistry, you're not going to dissolve all of those elements with aqua regia. You'll get almost all of them with 4-acid digest if it's done at a good lab. You'll get pretty much all of them if you do a fusion and then a digest after that. But there are things that you'll miss out on if you do a fusion digest. So if we have a look at that, we can see the difference here between an aqua regia digest, where we're just not dissolving either our silicates or our resistate minerals like zircon, versus a 4-acid digest where we are. With some 4-acid digests, and particularly where you've got zircon, zirconium sitting in zircon rather than other minerals, we'll tend to see that the lithium borate fusion, which is fusing the sample to glass before that you try and dissolve it, so you're overcoming those mineralogical controls. And so we'll see really poor dissolution in some cases with the 4-acid digest relative to the lithium borate. But there's a really big lab control on that. So this is an example here comparing two different labs. So this is a 4-acid digest, essentially the same process on the face of it. This is at a good lab who's got good practices and done things properly, and where we're dissolving everything into solution before we run the final analysis. And you can see how much you can discriminate here in these different rock units. This is from the same area where we're seeing the same rock units. And all we've got is this overall messy kind of cloud. So it does matter where you get your samples analysed. When we're looking at the finish we use, it's really important to consider this both in terms of the elements that we can analyse for and the detection limits, particularly with our Pathfinder elements. Analyses that are done historically or at the moment by things like AES or OES analysis methods, you don't get the detection limits that you need to fully resolve anomalies in these elements compared to their typical crustal background. So if we take bismuth, for instance, so if you get 4-acid digest with an ICP OES finish, you might get a detection limit of 2, but the average crustal abundance of bismuth is about 0.1 to 0.2 ppm. So you're not going to see bismuth until you get, orders of magnitude above the crustal background, and where you've already got quite a significant anomaly. If you use ICP-MS finish, you'll get detection limits that allow you to see and image essentially all those changes in concentrations. So that's an example there of what, that's a bismuth anomaly with ICP-MS data. This one here is with ICP-OES. A couple of final points, I guess. Data wrangling, you've also always got issues with it. I'll keep moving on given the time, but always allow time for data wrangling because it will always be significant. And with visualization, pattern recognition is what this is all about. Give your eyes the chance to see the patterns. So, don't do this, do this. Put it in the context of the geology, use maximum intensity projection within Leapfrog. If you're using that program, give your eyes the chance to see the patterns before you go in and try and explain them and work out whether they're real or not. All right, I've got a few other things there, but I'll be able to provide this presentation to people if they like, and I'll finish up. Thanks very much.